Okay, so last time we had our section on 5.1, we were talking about discrete and continuous random variables. Today we're going to focus on specific types of discrete variables, specifically the binomial probabilities. We'll cover that in 5.2 and 5.3, and then in section 5.4 we'll talk about the other two. So the binomial one is certainly the biggest of the three. It's the most useful and the most relevant, and you see it the most kind of in real life scenarios. So we understand the idea generally of discrete distributions, and so now we're going to get specific to binomial probabilities. Well, what is a binomial experiment? Well, a lot of times when you do some kind of situation, whether you're playing a game of chance or doing some kind of selection process, the situation arises where you either have something that happens or it doesn't happen. And so since those are two possible outcomes, those are called binomial experiments, right? Two outcomes, binomial. So there are 5 features that are sort of required to qualify as a binomial probability. And the first one is that there are a fixed number of trials. That means I know in advance how many times I'm going to do something. So when you see the symbol n, that tells you the number of trials that are going to occur. One thing we have to keep in mind is that those trials are independent. So the easiest example I can come up with is rolling dice. If I know I'm going to roll 5 dice or one die 5 times or whatever, and I know that the outcome of one doesn't impact the outcome of another, right? And so we're going to make those independent outcomes easier to compute, okay? Again, as we mentioned, it's binomial, so there are only 2 outcomes. Now we call them a success. It doesn't necessarily connote anything successful, but that's what the thing you want to have happen is a success, and then the thing you don't want to have happen is a failure. So we'll see S's and F's a lot to represent that, okay? And so one thing we want to do to make things easier to compute is to know that the probability of each success is the same, right? It sort of makes sense. You want to make sure that the probability you're doing is going to have the same outcome every time you try it, okay? And we use the letter P to denote the probability of a success and Q to represent failure, right? So success is P, failure is Q, right? And so together, you'll get 1, right? Either you succeed or you fail, there's nothing left, right? So the 2 of them together add up to 1, all right? And so what we want to figure out is we want to know how many successes occur out of a fixed number of trials, all right? So that's what the goal is. And these examples here in this section are pretty much just rinse and repeat of that scenario, okay? And so the first example talks about blood types of people here. And so we know somehow that based on a textbook that 9% of the population has type B blood, all right? So if we choose 18 people, and there's our fixed number of trials, 18, and we test the blood type, what is the probability that 3 of them have that blood type B, okay? And so we're going to assume that those are independent and that one person you select has no outcome on the other, right? So we're going to assume that these 18 people have nothing to do with each other. They're independent. We know that there's a fixed number of trials, and this is the number of successes we want, okay? So in this experiment, we're observing whether or not they have type B blood. We call that a success, right? So if you have type B blood, you're considered a success. So then obviously the failure is that they don't have type B blood, right? A person does not have type B blood. Pretty straightforward, okay? So the probability of success is 9%, right? We talked about that. So what is the probability of failure? We call that Q. And of course, that's 1 minus P, or 91%. All right, pretty straightforward. How many trials are there? Kind of said that at the beginning. There are 18 people selected, so there are 18 trials. So we want to know the probability that 3 successes exist. And so we call that letter R. So R is the number of successes, and so you have 3. The question is, which 3 out of the 18 are the successes? Right? If you numbered them A through whatever the 18th letter of the alphabet is, then you could have ABC, ABD, ABE, and you could have all the different outcomes for 3 people. And that's what leads to this next section. So if you're taking a final exam and you have 3 multiple choice questions left, right? You know that there's 4 answers on the test, and only one of them, of course, is correct. Now, if you only have 5 seconds left to answer them, you're not going to read them and try to figure it out. You're just going to quickly mark something on there without even reading the questions. So they're basically random, right? So what's the probability that you will get all or none or anything in between correct? This is a binomial, right? So each question is a trial. So each question is its own thing. So there are 3 of them. And the possible outcomes are a correct response, which is a success, and an incorrect response, which is a failure. Right? They're independent of each other. One outcome has nothing to do with the other. And so we can think of this as a binomial scenario. What's the probability on any one question? Well, there were 4 to choose from, right? There were 4 answers from which to select. So the probability of of getting it correct is 1/4, 0.25. Obviously then, there's a 75% chance that you'll be wrong, all right? So putting it all together symbolically, we have n is 3, p is 0.25, and q is 0.75. That's all we need to figure out the probabilities. Now, question is, what are all of the possible outcomes, right? So if you think back to what we did in section 5.1 and even in unit 1, we want to list all the possible outcomes. Well, either you're right or wrong, right? You're either successful or you're failing. So those are going to be the 2 things we have. And we know when we have 2 things done 3 at a time, there are 8 outcomes, right? So just like coin flipping or genders of kids or whatever, you have these 2 outcomes. So either you have them all correct, or you have them all wrong, or every possibility in between. Maybe you get the first 2 right and the third one wrong. Maybe you get the first and the third right. Maybe you get just the second and the third right. Or maybe you get the first one right and the other 2 wrong. Or maybe the middle one is right. Or maybe the last one is right. So these are your 8 outcomes that you can get of those 3 questions. You can get them all right, all wrong, or somewhere in between. And we use the thing we did in chapter 4, the multiplication rule, because they're independent. So specifically, if you want the probability of success on the first 2 questions and a failure on the last. First 2 questions success, failure on the last. Well, that's going to be this specific outcome. First 2 questions and the third one wrong. Now, it's not 1 out of 8. They're not equally likely to happen, right? If this was equally likely, the answer would just be 1 out of 8. But we know that the probability of success is only 25%, not 50%. So we can't just say 1 out of 8 because they're equally likely. We have to figure out them individually. So the probability of a specific outcome is the first one is a success, that's 25%, and the second one is a success, 25%, and the third one's a failure, or an incorrect answer, 75%. And if you multiply those 3 probabilities out, you get about 4.7%. Which means to say that to get specifically the first and the second one correct and the third one wrong would have happened just under a 5% chance, okay? Well, that's one specific outcome, right? You don't want to know that specific order. You want to know every scenario where you would get 2 right, and then every scenario where you get 1 right, and all the rest, all right? So think of this in terms of a random variable like we did in 5.1. How many successes out of 3, right? We did the coin flipping example for that carnival thing. There were 0 ones, 1 1, 2 1s, or 3 1s. So that's what's going to lead to our scenario, right? So if you were to figure out the probability of all 3 correct, you could do it, right? It's tedious, but not terribly complicated. You could do 0.25 times 0.25 times 0.25, and you would get 0.016. So a 1.6% chance of getting them all right. And you can do that for every single outcome. As you can see, definitely tedious, right? So you could do that if you wanted to, and because I did it ahead of time, I know that the answer here is 0.047 and 0.047 for those specific outcomes. So SSF was 0.047, but so is any other scenario where you have two S's and one F. Well, you could do this for all of the outcomes, but it gets a bit tedious. And so there's a formula for it. Now, I'll give you the formula and kind of explain it, but at the end of the day, you're going to be able to use your calculator. If you remember from the previous unit, we had a combination button, the NCR button. And this tells you the number of successes out of a number chosen, right? So this is a combination of N things chosen R at a time. We're going to use that as our coefficient. So we call this the binomial coefficient. And this will tell you how many ways you can get a certain outcome. And then you're going to take that coefficient and multiply it by the specific value there. So like for that instance, we have that. So we could have the probability of our outcomes. So in this case, let's say we have 2 successes. We would have N choose R, so that's the number, times the probability of success and how many times that success occurs. And then you'd have the failure and how many times it occurs. So in this case, we would have N is 3 questions. We want 2 correct answers. We take that number times the probability of success to the second power, because we want 2 successes, and then the probability of failure to the first power, because we want 1 failure. So this probability, 0.25 squared times 0.75, that's what we did up here, right? 0.25 squared times 0.75. All we need to do is multiply it by the binomial coefficient, which is 3, right? There are 3 ways that we can get that, times 0.047. And that will give us our final answer, right? So if you did it by hand, you can do it. It's certainly possible. You'd have to use your calculator and kind of multiply all of that out, but you would get approximately 0.141, right, depending on how you rounded. So there's a 14% chance that you would get 2 out of the 3 right, no matter what the order is, okay? So let's take a look at a little bit more thorough example, and then we'll show you how to do it on the calculator, okay? So in this example, they talked about 59% of internet users who are concerned about the confidentiality of email, okay? So what's the probability that in a random sample of 10 users, 6 are concerned? Exactly 6. So again, N is 10, R is 6, and the probability of success is 59. And now you just plug everything in. So you have 10 people chosen 6 at a time, because that's what you want in terms of the coefficient. How many ways can you pick 6 people out of 10? 59% success, that's going to happen 6 times, right? Person 1 times person 2 times person 3 times person 4 times person 5 times person 6, which then implies that the other 4 people who aren't concerned are considered your failures. Notice the exponents always equal n, right? So keep that in mind. 6 plus 4 equals 10. So that's a nice little check for you, all right? And furthermore, this 6 should always match the 6 on the first exponent. So you can multiply all that out, and you would get 210 for this, times 0.0422 for that, and 0.0283 for this, gives you about 25%. That's kind of a lot to do on your own. You have to find your NCR button. So if you have your calculator out, you want to look at where the math, prob section is, right? So you'd have to go to NCR, you'd put a 10 there, and then you'd go here and put a 6 there, and then you'd multiply it by 0.59 to the 6th, and then you'd multiply that by 0.41 to the 4th, and you can do all of that, and you get your answer, about 25%. But there's a faster way. And that faster way is to use another function on your calculator under the math option called PRB. Right? So if you go to your calculator and you press the math button, if you go to the PRB, that's where you get your NCR option. Okay? So that's Math Prob 3, you got that. Okay? But there's an even better way to figure that out. And that's under what we call a binom PDF. A binom for binomial probability density function. Now this is a new place on your calculator. If you go to your stat button, your vars button, and you want to go to second vars, you will see it. And we'll do this next example kind of together that way. So second vars, you want to go all the way down to what's called a binom PDF, which is option A. All right? So we're going to kind of do this next example, example 3, using the same idea, all right? And I think you'll see kind of a nice, easier way to do that. All right? So in this example, we have a scenario where you have a 30% success rate for an operation for an eye operation, okay? And so we want to see that it's been successful in 4 out of 6 operations. So you have 6 operations, that's your sample. What's the probability that 4 were successes? Okay? And so we're going to figure out if it's likely that the new technique is better than the old, right? This new technique had 4 out of 6, but we want to see if it's any better than the original 30%. So we have an N is 6 people in there, and the probability of success is 30%. So that means the probability of not succeeding is 70%, and we want to see if there were 4 successes. All right? And so the old-fashioned way to do it is to take 6 people, choose 4 of them, multiply 0.3 to the 4th, and multiply 0.7 squared, right? The sum of the exponents equals n, and that first exponent is r, all right? And if you can multiply that out, you can take some time, pause the video, take a check on the calculator, and you'll get about 6%, okay? Now, if you do it with this new method, if you go to second vars A, you'll see binom PDF. So let's take a look at what that's like. So if you go to second vars, you'll scroll down and eventually you'll see binom PDF. Now, depending on your calculator, it may prompt you for some information. On this online version, it asks you for the binom PDF, so the number of trials is going to be 6. The probability of success was 0.3, and you want 4 successes. If you do that, and you get 0.0595, which rounds to 6%. Okay? So that's the easy way to do it. In terms of showing your work, you still want to show the formula, right? So you still want to show the numbers plugged into the formula, but then you can let your calculator do the binom PDF version and give you the answer, right? So we need to see the work. We can't just see binom PDF with a bunch of numbers thrown in, okay? So show me the formula and you'll be all right. As we get more and more comfortable with it, I'll show you some scenarios where you don't need to do that. But for now, let's just keep that in there, okay? And so that's the idea for a specific outcome. Now, maybe you want to know an interval. So in part C, we want to know the probability of at least 4 successes, which means that's greater than or equal to 4. So not only are you computing the probability of 4, but then you're also adding 2 more probabilities. And this gets a little bit lengthy, right? We know that the probability of 4 we just figured out was 0.0595. If we did the probability of 5, we would get 6 choose 5 times 0.3 to the 5th times 0.7 to the 1st. And that's about 1%. And then we would do the probability of 6, which is 6 choose 6 times 0.3 to the 6th times 0.7 to the 0, which gives you about 0.001. And what you would do is you would add these 3 probabilities up to get your final answer, and the sum is going to be about 0.0705. Okay? And that would be your probability. Now, there's another term for this on your calculator. So we talked about the binom PDF key, right? So the binom PDF key occurs when you want an exact outcome. We want exactly R to be a specific number. In this case, in part B, you wanted it to be 4. If you want an inequality, you can use what's called the binom CDF. And that is, of course, if you're going on there, that would be your second vars. And then you would go to option B. Second vars B gives you the CDF. And C stands for cumulative, kind of like when we did cumulative functions in the histograms. And what this means is, if you use the CDF, you're going to compute R or fewer successes. All right? So again, here's a little screenshot of the binom PDF when you had exactly 4, right? That was this example up here, 0595, right? When R equaled 4. If you want CDF, this is the probability of 4 or less. So notice it's a much bigger probability, because this is the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4, which is a lot more annoying if you do it by hand. So the CDF function allows you to do the calculator to find the answer. Now, to get our answer from part C, we wanted it to be greater than or equal to 4. The CDF is limited. It only gives less than or equal to 4. So my advice to you is to kind of list out the outcomes, right? You know there were 6 total. These are your different outcomes. You could have anywhere from 0 to 6 successes, right? The CDF says take 4 or less. It calculates that outcome. If you want 4 or less, that's the complement of 5 or more, right? You either have 4 or less, or you have 5 or more. So if you wanted to do the answer to part C, so the probability of R being greater than or equal to 4, you would have to use these numbers. Now the calculator doesn't go greater than, it only goes less than. So you would have to use binomial CDF for 6.3 and then 3. So it gets a little tricky here. If you're using the CDF, you want the values 3 or less to come up. And then you have to take the complement. So then you would take the answer here and subtract it from 1. All right? So it's kind of a tricky version if you want to use your calculator, and obviously I'll be here to kind of explain the calculator more thoroughly over the next several courses of classes. So just keep that in mind. So the calculator only gives less than or equal to, right? That's the key takeaway from this, is if you want to use the calculator, the CDF function only does the number or less. So if the question asks for something less than, 4 fewer, at most 4, no more than, whatever, then you're good. You can use your CDF function for R equals 4. Great. If you want greater than or equal to 4, that's trickier, right? So that means 4 or more, which means you have to have a CDF where R is 3 or less, and then subtract from 1. Okay, that's the idea. Okay, so if you did the binom CDF from up here, and you did 1 minus, let me just do it down here for space purposes. You could do 1 minus the binomial CDF That's 6.3 and 3 on your calculator. So if I take my calculator here and I go 1 minus second vars, binom CDF, N is 6, P is 0.3, R is 3, remember we want 3 or less, that gives us 0.705, right? So it's a little bit more legwork, and you really have to understand how the calculator function works if you don't want to do it by hand. My advice, always do it by hand to get the idea and add them up, right? 0.07047, 0.705, just a rounding thing, right? The calculator gives less than or equal to R, in this case 3, and so then you've got to subtract that from 1 to get the correct answer, okay? And then just to further this along, you have to be careful of the intervals. If it's less than 4, you have to use R equals 3, right? Because R less than 4 means R is less than or equal to 3, all right? Because remember, these are countable things. If you have less than 4 successes, you have 3 or fewer successes, right? R greater than 4 means R is 5 or more. R greater than 4 means 1 minus R less than or equal to 4, because that's R greater than or equal to 5. Greater than 4 means 5 or more, which is the complement of 4 or less. So really understanding that complement idea from last unit is helpful. All right, so I know it's a bit confusing, so try your luck on the calculator, but you should be okay after a few attempts, okay? The last thing is the next section is 5.3. Some simple, quick formulas for the means and standard deviations, all right? Do that really quickly, and then we'll be in good shape, all right? So special formulas, which will be given to you, right? So don't worry about memorizing these. The mean of the scenario in binomial, right, mu, is simply the number of trials times the probability of success. Think of this as the expected number. So if I'm shooting a basket 10 times and I'm a 30% free throw shooter, you would expect me to have 10 times 30% chance of getting it in, gives me on average 3 baskets, right? And that's what we mean by that, right? So you're just multiplying the number of trials times the probability. The standard deviation is a little more complicated formula, but there's your sigma again. Square root of n times p times q. So these formulas will be given to you. You just have to look and see if it's a binomial setting. Then you just plug the numbers in and you're in good shape. So here's that example I was kind of referring to before, a basketball example. Let's say he's a 50% shooter, right? So out of 6 throws, what's the expected number of field goals he makes? It's simply n times p, 6 throws, 50% make. He should make 3 field goals, right? What is the standard deviation? You simply plug in the numbers, right? Standard deviation is 6 times 0.5 times q, which is also 0.5, which is 1.22 field goals. Okay, so that's pretty straightforward. You can find the mean and standard deviation simply by plugging those formulas in, and then we kind of ask a follow-up question. So we kind of talk about Chebyshev's theorem. This showed up on the test. We can use this sort of general gauge for 75% standard deviations. For binomial scenarios, it's 2.5 standard deviations, okay? And so what you can do is you can find, if you're given n and p, identify the mean, 20 times 0.7, which is 14. The standard deviation, which is 20 times 0.7 times 0.3, is 2.05. And now you can plug those into the formula here and here to find the boundary values. So you expect them to make 14 baskets, but there's of course going to be some variability, right? So on average, he'll make 14 baskets, and you're willing to give him a little bit of wiggle room, like, all right, well, maybe he had a good day or a bad day. So the lower boundary is going to be 14 minus 2.5 times that, which gives you 8.875 baskets. And the upper boundary is going to be 14 plus 2.5 standard deviations, which is 19.125. All right, so you're willing, according to this rule, to give anywhere between 9 and 19, right? So it's unusual, at least mathematically, if there were fewer than 9, right? So if he makes 8 baskets, you'd be like, wait a minute, you said you're going to make 14. You're a 70% free throw shooter or whatever, and you made 9? That's not good. Or above 19, which means essentially he makes them all, in which case he's better than a 70% shooter, okay? So that's sort of your boundaries for that. Remember, 8.875 really is 9, and 19.125 goes down to 19. So anything beyond those values would be considered unusual. All right, so that's sort of a quick version of the notes. I, of course, will be available for any questions, but it's very computational, so hopefully it makes some sense to you, and let me know if you have any questions.